Okay. Now we are going to understand how to use this gap effectively, right? So for that, let's go back to basics and see what we have, right? So we had A, which is an M cross D matrix, and if I had done the SVD of this, I would have gotten U sigma V transpose. Now, of course, I am trying to approximate the basis for U, right? So the top k vectors of U. Now let's look at this matrix A transpose. What would this matrix be? Well, A is U sigma V transpose. So this is going to be U sigma V transpose times U sigma V transpose transpose, which is U sigma V transpose. V transpose is V. I mean, when I take the transpose, I have to read it out in the opposite direction. And then sigma transpose, remember sigma is diagonal, so sigma transpose is just sigma times U transpose, and this is just U sigma. V transpose V is I because V is an orthonormal basis for RD. Sigma into sigma will become sigma squared, and this is U sigma square U transpose. Now let's look at the following. Let's ask what is A transpose times A. I'll try to explain why we care about this in a minute, but let's say we ask this question, right? So now we know A transpose is U sigma squared U transpose times A itself by SVD is U sigma V transpose. So this is just U sigma squared U transpose U sigma V transpose, which is U transpose U is I because U is an orthonormal basis for RM. Sigma squared into sigma is sigma cube into V transpose. So A transpose A is U sigma cubed V transpose. Now why is this a useful observation? This is a useful observation because of two reasons. One is, amazingly, for A transpose A, the left singular vectors that we care about is exactly the same. The U has not changed. Of course, the right also has not changed, but we don't worry so much about the right in this case, right? So we care about the left singular vectors. That has not changed. But what has changed are the singular values. Earlier, you know, the singular values were sigma 1, sigma 2, and let me make it, you know, greater than this, sigma k, k plus 1 dot 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 sigma d. Yeah, so the remaining are zeros. Now what has happened is, because this is sigma cubed, so this is going to be, everything is going to get cubed. But, well, the relative inequality is going to stay because everything gets cubed, and these are all positive values, so nothing changes. The equality remains the same. Oh, sorry, did I change it? Yeah, so this is still going to be greater than this sigma d cube. But the advantage is that, I mean, the biggest advantage is the following key insight. Now, all I wanted to do was do the SVD for A in a fast manner. But now I observe, if I do A transpose A, I get U sigma cubed V transpose. Now, if I had done a sketch for A transpose times A, which means that if I had computed, let's say, y equals A transpose A times omega, that is, if I treated this new matrix A transpose A as my given matrix, and then I did a sketch for that by multiplying it with random linear combinations, and then I did an orthonormalization of, you know, y to get q, and I reconstructed the SVD as usual for A. Now, how good is this orthonormalization q that I get with respect to the actual q that I should have gotten, right? So now there I can ask, you know, so let me put this down, right? So now what I do is I get q by orthonormalizing y, and now I ask how good is q transpose with respect to the the left singular projection onto the top k left singular vectors of A transpose A, which happens to be exactly the same U, right? So, which is UK transpose. Now, we know that this depends on the gap between of the matrix that we care about. In this case, the matrix that we started off with is A transpose A, which means that this is going to be sigma k plus 1 of this matrix divided by approximately, of course, sigma k plus k of A transpose A. But we know how these singular values are related to the singular values of A itself, right? So, now that would just be, this is just sigma k plus 1 of A by sigma k of A whole cubed, because the singular values have cubed. Now, the question is, what is this, how does this value compare to our earlier approximation, which is sigma k plus 1 by sigma k of A? Of course, I should put an A here. That was implied at that point, but now because we are using different matrices, let us make the matrix dependence explicit. So, sigma k plus 1 of A by sigma k of A versus sigma k plus 1 of A by sigma k of A whole cubed. Remember, sigma k plus 1 is smaller than sigma k, right? So, whatever it is, it's smaller than sigma k, which means that the ratio is less than 1, and now I am cubing it, which means that it's going to become even smaller, which means magically what we are saying is that instead of working with the original matrix A and then randomly combining the columns of A, getting an orthonormal basis for that, and then using that basis to do QQ transpose, we could instead work with the matrix AA transpose A. And what we are getting is a Q from this, and this Q will approximate the exact subspace spanned by the top k singular vectors much better than what we would have gotten had we used A itself originally, right? So, and it will the level of approximation will be even better if sigma k plus 1 is close to sigma k, which means that let us say sigma k was 1 and sigma k plus 1 was 0.9, earlier it was 0.9 divided by 1, that was the approximation that we had. Now it is 0.9 cube, right? So, which is much smaller than much smaller than 0.9, right? So, this would be something like 0.729, right? So, 0.81, 0.9 into 0.9 into 0.9, which is 0.81 into 0.9, which is 0.729, right? So, the approximation becomes better, right? So, now the question is, why can't we do this, right? So, now we seem to have a better method, right? So, and the second question is, why should I stop here of multiplying AA transpose? Now, this seems to be like a magic box, right? So, and then I can reuse this magic box multiple times, right? So, now for example, if I now do AA transpose raised to power some power q times A. Now, by the same argument, what we would end up getting is this will be u sigma power 2q plus 1 times V transpose. Why is it 2q plus 1? Because this sigma squared, now if I raise it to the power q, this will become 2q, and then there is 1 sigma that comes from A itself. So, this will be 2q plus 1 times V transpose. So, which means our approximation is going to become sigma k plus 1 by sigma k power 2q plus 1, and that is going to be much better. And now I can make this as small as possible as I want, which means that simply by using a different matrix, it seems like we can get a much better approximation for the basis that we are trying to approximate onto which we want to project, which is the top k singular vectors. So our algorithm then, our new or updated algorithm is going to look like this, right? So, now our algorithm will look like this. So, let us say I am going to set some vector C as A transpose power q into A, and now I will set y equals A omega as usual remember A is m cross T, so A transpose is m cross m, so power q will also be m cross m. So this is m cross m, this is m cross T, so C is still m cross T, right. So sorry, I will set y as C omega, and then what I will do is q is as usual orthonormalization of y, and once I have a basis which is a better basis for the top k singular vectors of A transpose QA, which is the same as A and which is what we want, I will now set B as the remaining is the same, Q transpose A, do SVD of B, get U tilde sigma V tilde transpose sigma tilde, and now pull back, right. So, U itself is Q times U tilde, U hat sigma hat is sigma tilde, V hat is V tilde, and approximation A hat is U hat sigma hat V hat transpose. Now, this seems like almost magic, right. So, I mean, all we are saying is instead of working with A, instead work with A transpose power Q times A, and you get something for free. Now, the problem though in this case would be that we have to explicitly compute A transpose, and to do that what would happen is you have to multiply m cross D with D cross m, right. So, and you will have to take order of m D squared, and that beats the purpose. So, while this seems like a cool idea, but then just to compute A transpose, and of course you have to raise it to the power q, let us say that's not going to be so hard, I mean that also is going to depend on something like m squared, which is also prohibitively large. So, while there is this interesting matrix which captures what we want, we cannot compute this. So, in other words, we cannot directly compute this, right. So, but if there was a way to somehow mimic what we are doing here as A transpose power Q times A, then computationally if we can do it faster and still mimic the effect of A transpose power Q times A, and then linearly combining columns of that, then we in fact we gain, right. So, computationally we gain, and the answer to this is yes, we can do this, and we will now put down the final full blown algorithm for randomized SVD, which includes this new technique. Well, it's not a very hard technique, but but the reason why we are doing it is for computational efficiency. It's called the power iteration, and the algorithm now is as follows, right. So we have A, which is in R m cross D. So let me give the name to this. This is randomized SVD with power iteration. What we do is we compute y equals A sigma. We are not doing A transpose power QA explicitly, we will do that implicitly using a trick. And now we are going to do what is called as the power iteration. So, which is for I equals 1 to q, what we are going to do is we are going to orthonormalize y, get q, and now we are going to compute, essentially we are going to compute A transpose q, but then we are going to do it in two steps. We will do z equals q transpose A, and then y, we will set y as A times, we will set, z equals A transpose q, and we will set y as A times z. I will explain this in a minute, right. So this is the power iteration part. I'll just explain this in a minute. So this is the power iteration, and once we do this, what we have is at the end we get a q, and once we have that q, everything else is the same, right. So then we will set b equals Q transpose A, and we will do SVD of B. B equals U sigma, I mean I keep repeating this, but that's good to know. So, then you pull back U as Q times U tilde, and then you set A hat as U hat sigma hat V hat transpose. Everything else remains the same. The only thing that has changed is this part, which is the power iteration. So, basically what we are doing is we start with A, and now we are getting this Q out of it, and remember, so A is M cross D, this is D cross L for some L which is K plus P, where P is the oversampling parameter that we saw earlier. So, this is this step is as usual going to take MDL, and that is still okay for us. Now, I am doing an orthonormalization of Y, and what is Y? Y is M cross L. So, this is going to take ML squared, which is still okay for me. So, the Q that I get here belongs to what? So, Q belongs to M cross L, right. So, because this is so basically I have a orthonormal basis for these L vectors, that's basically I had these L vectors, but then I create an orthonormal basis for that. Now, Z is A transpose Q, right. So, A transpose is D cross M times M cross L. So, that is still order of MDL, which is okay for us, and Z itself becomes D cross L. And now I do A times Z, which is M cross D times D cross L, which is again order of MDL, and then Y now becomes M cross L, right, M cross L. So, effectively by doing these two steps, what I am doing is, Z is just A transpose Q. So, if I substitute A transpose Q here, I am just doing Y as A transpose Q. And then I am repeating this small q number of times, which means that essentially what I have done is I have done A transpose power q, right. So, that's precisely what has happened, and because of this, this is like mimicking starting with A transpose power q times A, and then getting a q for doing a random linear combination of those columns, and then orthonormalizing it. Well, we are doing this in q steps, right. Of course, this is the whole thing is going to take order of MDL times q, because we are doing this q times, right. So, well, now there is a trade-off between how many times we should do. Of course, more number of times I do this, the better approximation that I get, but then I also suffer in terms of the computational complexity. So, that is there a trade-off that I need to work with. But now, because what has happened is, so why does this work geometrically? So, geometrically what is happening is the following, right. So, earlier I had A, which was sum over I equals 1 to D. One way to write A would be to write this, right. So, Ui Vi transpose, where Ui and Vi are the singular vectors. And now, when I did A omega, which means I did a random linear combination of the columns of A, then that would just be sum over I equals 1 to D sigma I Ui Vi transpose omega, which means that I have these Ui's, which are the left singular vectors. Each Ui is multiplied by the corresponding sigma I, right. So, the top k guys would have more energy in this linear combination. Of course, then I am combining it with a random linear combination Vi transpose W, that's there, but then Ui itself gets multiplied by sigma I. That is what was happening earlier. Now, what is happening is, now we have something like A transpose power q times A, which is sum over I equals 1 to D sigma I power 2q plus 1, right. So, that is the power that sigma I gets raised by Ui transpose Vi transpose, that remains the same, both the left and the right singular vectors do not change. So, when I do A transpose power q times A times W, now I get sum over I equals 1 to D, okay, erase this by mistake. So, this was sigma I Now here it would be sigma I power 2q plus 1 times ui vi transpose w. In other words, the larger sigma gets blown up even further than smaller sigmas, right. So, the linear combination is going to focus more on larger ones basically, right. So, the energy will be concentrated more with the larger, the ones with the larger sigma. And so, you are kind of separating out the difference between the top k and the top k, k plus first directions even more, so that you will get a better approximation for the projection onto the top k. That's precisely is what is happening. Of course, we already saw that if I do this, then my QQ transpose minus UK transpose L2 norm is going to be sigma k plus 1 of A by sigma k of A power 2q plus 1. It's going to be a much better approximation for the projection operator, and because it's a much better approximation for the projection operator, one can also argue that A minus QQ transpose A, right. So, which is finally how good a rank K approximation of the SVD, the approximation for the SVD that we are getting via this method, how good is it representing A itself? Well, we can represent this as, remember earlier it was 1 plus epsilon times sigma k plus 1 of A. Now, it is going to be 1 plus epsilon power 1 by 2k plus 1 times sigma k plus 1 of A. You can work this out as well, right. So, basically what we are saying is that this number is going to be much smaller, right. So, you still have to suffer sigma k plus 1 of A. I mean, there is no, you cannot do better than what the naive SVD gives you, right. So, but then how much worse are you with respect to the naive SVD depends on, how much extra that you are suffering, right. So, this is sigma k plus 1, which is something that you cannot get rid of. That is something that any rank K approximation has to suffer. But the extra that I am suffering now is like this epsilon prime, which is epsilon power 1 by 2q plus 1 times sigma k plus 1 of A. Now, even if sigma k plus 1 of A is large, right. So, earlier without the power iteration, we would have suffered a large extra additive approximation constant. But now, because of this Q business, now this value will compensate for the large value of sigma k plus 1 of A, and still we can bring down this value to as small as possible that we want. But if you want to bring it down to as small as possible, then that means that you are suffering here in terms of the number of times you are running the power iteration. So, that is a balance that we can strike. So, in full-fledged glory, so finally this is the randomized SVD algorithm. So, let me summarize this. All we wanted to do was we started with the matrix A, huge matrix, we wanted to do SVD of it. The trick is to find an approximation for the top K subspace of A, and to do this we are using the power of randomization. We are randomly combining the columns of A and we are finding a basis for these random linear combinations, and this basis will approximate the real basis that we want. Now, the quality of approximation depends on the gap between the kth singular value and the k plus first singular value. So, to amplify this gap, what we are doing is the power iteration, right. So, we instead of working with A, we work with A transpose power q times A, where the left and the right singular vectors are retained. So, the subspace that we are approximating is exactly the same, but the quality of approximation that we get depends on this gap which now gets amplified, and so the quality of approximation becomes better, right. So, and of course, you pay a price in terms of computation for power iteration. So, this is the randomized SVD, and it is a very commonly used tool in practice. Implementing this is super easy, right. So, you just have to do QR decomposition, you should do SVD, of course, there is an SVD component, but then a lightweight SVD, and then multiplying by Gaussian matrices. But the reason why it works beautifully is because of this geometry that it gets captured by random Gaussian linear combinations, like how Gaussians helped with respect to distances in JL, with respect to the bucketing in locality sensitive hashing. It helps with respect to preserving the top K subspaces with respect to SVD. So, this is the randomized SVD algorithm. So next time I will meet you with a different algorithm, different problem, where we will still work with, hopefully we'll see the power of randomization in other areas of data science. Thank you.